Hello, welcome to an NMR tutorial on NMR multiplicities and splitting, or why is the signal that shape? Just to outline what we're going to talk about, I'm not going to talk about chemical shifts. I believe you're already familiar with that. Instead, I'm going to focus on splitting patterns. So we take these signals here, we're going to talk about why they split, why the couplings are the size they are, and why the line intensities are as you see. We're going to talk about how the splittings arise, what influences them, and what information we can gain from them. I'm also not going to talk about why these aromatic protons are at nearly 10 ppm, but maybe we'll come back to that in a later talk. So the format's going to be a quick summary of how NMR works, some discussions of the origins of splitting, and then finally what influences the observed J values. So let's start with the concept of nuclear spin, which is the origin of NMR. Some nuclei have spin, and this is a fundamental property denoted by spin quantum number. This is a physics analogy. It has nothing to do with the spinning of a football, a cricket ball, tennis ball, or whatever. That said, if it helps you to think of it that way, feel free. Before we move on, I just want to point out that organic chemists usually talk about electrons. And although they are relevant to this topic, we're going to be focusing today, at least at the start, on the nuclei. So, nuclei with non-integer spins, a half, 3/2, 7/2, are NMR active. However, the nuclei normally of interest to organic chemists are spin a half, which is good because it makes our lives much simpler. So examples of this include protons, the carbon-13 isotope, fluorine, and phosphorus. And spin a half nuclei has two orientations, plus a half and minus a half, up and down if you prefer. In the absence of a magnetic field, there are equal quantities of each. In the presence, however, of a magnetic field, these are aligned with and against the field, like the poles of a magnet. You can see here how this energy gap grows as the magnetic field gets stronger. This is called the Semen effect, and this changes the equilibrium position between these two spins and creates an equilibrium where there is a small preference towards aligning with the field, and this results in a net magnetization. A radio pulse then scrambles this distribution, and energy must be lost to return to the equilibrium position, and it's this process that we record and turn into NMR spectra. So to go over that in a little bit more detail, here we have 3 spin-a-half nuclei, and we're going to add to that 2 minus a half nuclei. This gives us a net polarization in line with the field along what we call the z-axis. I should say here the preference in real life is much smaller than that. It's maybe a 6 atom preference in a million, but it's enough. Okay, so in reality, the nuclei, the spins can't orientate just straight up the z-axis, and they precess around this in a circle. However, the bulk magnetization is still along this axis. We then use a radio frequency pulse to generate a magnetic field at 90 degrees, and this flips this orientation, so it is now in the x or y axis. It will then precess around this circular fashion, returning to equilibrium. And that's the relaxation process. In doing so, it generates magnetic fields its own, and those we can record and use for the NMR spectra. This is a bit clearer, I think, in video form. So here we have polarization, and then flip onto the y-axis, and precession back to the equilibrium magnetization. So, to recap, the magnetic field makes our spin states inequivalent, causing bulk magnetization. We then push this from equilibrium with a radial pulse to an excited state. How does this compare to other spectroscopy? So for example, in absorption spectroscopy, we measure absorbed energy, and we correlate this to the presence of bonds or electronic features. In fluorescence, we instead generate an excited state, and we measure a photon which is re-emitted in a relaxation process. This process is quite slow, and we can only see fluorescence for some molecules. This is a sort of general feature, actually, spontaneous emission being somewhat slow, and it is actually energy dependent. It's dependent on the inverse cube of the energy. And NMR transitions are quite low in energy, and therefore spontaneous relaxation is actually very slow. Instead, relaxation occurs via interaction with other magnetic fields, be it that imperfection in the NMR field or the presence of other magnetic fields from other nuclei nearby. So this seems like a good time to mention spin-spin coupling. Spin-half nuclei within a certain range can interact with each other, and this happens through electrons and therefore through bonds. To give you a quick example of what that looks like, here we have a hydrogen molecule, and in the absence of any magnetic field, we can see that these actually prefer to be in an anti-parallel spin state, because this allows them to spin pair with the electrons on each side of the bond better. We then add an atom and a bond and go to this geminal type system. I'll explain what that means in a moment. Then the principle is the same, but you now want parallel spins, which is favoured. If you take it an atom further, you then end up back in an anti-parallel system. So the range of this varies, but 2-bond, which are called geminal couplings, and 3-bond, which are called vicinal couplings, are common for protons. Where orbital overlap is better, like in conjugated pi systems, the information is transmitted between nuclei better, and you can get longer range 4 or 5-bond couplings. And because all of these paired spins still have themselves a half and minus a half spin states, they then cause a split in the signal. And I'll now talk about what that means. So to depict the simplest possible example, coupling within a hydrogen molecule, in the absence of a magnetic field, which we can see here, the spins are degenerate and the energy is the same. Applying a magnetic field splits these. Since NMR measures transitions, there is one transition here, and there's a single line, which is a singlet. So if we then introduce the other atom, so now we have our 2 hydrogen atoms, which is a hydrogen molecule, there are now multiple transitions available. So you can go from here to here, from here to there. It is a feature that you generally only see single quantum number transitions. So here you're going from +1 to 0 if you add up the halves and minuses, and so this is allowed, but you're not, at least in this system, going to be seeing that. As a result of this, the nuclei being identical means that the transitions within the more complex splitting are actually all identical. This still gives you a singlet. Let's look now at an AX system, the A and X just meaning the chemical shifts of the two protons are quite different. This is a 3-bond vicinal coupling. All of this bit is as before, so we have splitting caused by the magnetic field, resulting in transitions between spin states. If we put both of our nuclei of interest here on the same diagram, but we don't couple them, then we can see each in this case gives a different transition. These are two different signals with different chemical shifts. However, if we look at the transitions available to atom A, which is here in green, and then the transitions available to atom X, in purple here, and in purple here, although they are not, those are between the purple and the green, both of the greens are equivalent transitions and both of the purple are equivalent transitions. They have the same energy, and so only a singlet is observed for each nuclei, and so you see two singlets of different chemical shifts. Now let's consider what happens if we couple these. So, in the absence of a magnetic field, because our nuclear spins like to pair with the electrons, as previously described, this is the lowest energy spin configuration. It's anti-parallel. When we apply a strong magnetic field, the preference will still be to align both of the spins with that field. However, because it gives us a less favourable spin interaction with our electrons, this is a little bit less favourable than it was previously. On the other hand, both of the anti-parallel arrangements are a little bit more favourable than they would previously have been. And then the alignment of both spins against the magnetic field is unfavourable because you're having to overcome both the unfavourable alignment with the magnetic field and the unfavourable electron pairing. The result of this distortion is that if we look at the two green lines for the A system and the two purple lines for the X system, we will see that there is now a pair of inequivalent transitions for each, and this results in each nucleus giving us two lines, so we see a doublet, different chemical shifts for each. If we consider the energy of that, as it happens, the distortion of each of these configurations from the uncoupled energy value is a quarter of J. If we start by considering atom A, we can see that for this transition, this anti-parallel state is a quarter of J more favourable than before coupling, and this state here, where both of the spins are aligned against the field, is a quarter of a J less favourable. The result of this is that the overall size of the transition is 0.5 J larger. If we then compare this to the other transition, exactly the opposite is happening. This alignment with the field is a quarter of J less favourable than previously, where this anti-parallel arrangement is a quarter of J more favourable. The result of this is that the energy of this transition is half J less. And this means that the difference between the two lines in total equals J. And what you can also see from this diagram, if you consider instead X, is that although the transitions themselves and the resulting chemical shifts are different from that observed for A, the difference between the two lines produced is going to be the same. So you will also end up with the J value as the difference between these two lines, and as a result, when we see your signal, it will also be a doublet, and it will have the same J value, and these are coupled. Okay. Let's take an example. Using ethyl acetate here, common solvent, and I have simulated the spectra, and we'll start with this acetyl group here. You can see our proton. We can count 1, 2, and 3 bonds. There are no spin half nuclei within 3 bonds, discounting the small prevalence of carbon-13. And as a result, these 3 couple to each other, but that all cancels out, and we see a single transition. If we were instead to take the other methyl group here, again, you can ignore the equivalent nuclei. 1, 2, 3. This couples to these 2 protons here. These are equivalent to each other, not to this. Now, if we look at how we can arrange the spins of these 2 protons, we have the parallel in line with the field configuration, that's the lowest energy, and we have against the field configuration, that's the highest energy. But there is an intermediate level, and there are 2 ways to achieve it because these states are degenerate. Because it can be achieved in twice as many ways, this transition occurs twice as often. And so when we look at the lines, we get an intensity pattern that goes 1, 2, 1, and gives us a triplet. If we then use these methylene protons here, so we focus on this one, again, ignore the proton that is equivalent. We go 1, 2, 3, split by 3 equivalent spin half nuclei. The same principle holds, but this time there is one more way of arranging these spins. So you can have 2 in line with the field and 1 against, or 2 against and 1 with. And again, these can be achieved in more ways. So now you have a pattern that goes 1, 3, 3, 1, and this is a quartet. Now, we really don't want to have to construct spin diagrams every time we need to understand an intensity pattern. Fortunately, we don't have to. We can use Pascal's triangle. So this is a scheme where the sum of the 2 numbers directly above gives the number below. So if you want, you can draw in 0 here. 0 plus 1 gives 1. 1 plus 1 gives 2, and so on. 4 plus 6 give 10. 10 plus 5 gives you 15. 15 plus 20 gives you 35. And in principle, so on all the way down to infinity. As it happens, we can take each number and we can consult the triangle, consult the row equal to 1 more than the number of protons we have splitting. So n plus 1. In the doublet, you have 1 proton splitting. Two lines, row 2, you can see a 1-to-1 ratio. You can instead actually just look directly at the number of lines. So triplet is row 3. And you can see 1, 2, 1. And this continues all the way down. A quintet is row 5, 1, 4, 6, 4, 1, and so on. You're really not going to see very much beyond this distribution in terms of splittings that are a single level and don't involve further coupling. So, in fact, you might already, if you're looking particularly closely, have been a bit thrown by the sextet. This is because a sextet should arise from 5 equivalent protons. Now you can't attach 5 protons to a carbon, and you actually can't draw a symmetrical molecule that splits 5 protons. So if I was to give you an example here and say that this is CH3 and that this is CH2, we have R. There's just no way you can actually make these equivalent. So I have got this particular signal simulated from butanol, and it's this proton here, and it couples twice there, give you a triplet, and 3 times here to give you a quartet. And this signal could also be considered a triplet of quartets where the J values are close enough that they overlap to give you this sextet. And in fact, this is a sort of general principle. You can construct signals this way. So 2 doublets, if they are separated by the J value, so they have another coupling of the same J value, add up to give you a triplet. 2 triplets, a quartet, and you can see you can add the line intensities and get the correct numbers. So a quartet arising from interactions with 3 protons here, so there we have it. Is equivalent to a doublet of triplets. And you can actually see this if you replace one of the protons with a fluorine. You're seeing coupling to the same number spin-half nuclei, but this J value is quite different. And what results is a doublet of triplets, where here we had a quartet. So their origins are the same, the differences in the J values. And in fact, all of these sort of composite signals, doublets of doublets, doublets of triplets, triplets of quartets, whatever, are constructed in this fashion. I just want to leave this slide with a particularly beautiful example. This comes from Anstey Group in Davidson College, and I'm just going to mark out, there's 2 quartets here, they're easy enough to see, but I will just mark them anyway. Okay, and what I want you to do is easy enough in your head is just imagine that you move all of these one place over. I think it's quite easy to convince yourself that what in fact you would see is a quintet with the correct intensity distribution. So we now understand, I hope, where J values, these splittings, come from, but what controls their magnitude? Why do we sometimes get large J values and other times small? Well, as we've already said, the spin pairing is mediated by the electrons in the intervening bonds. Good orbital overlap provides strong interactions and larger J values. Weaker interactions and long-range couplings are usually weaker and give you low J values. Now, the relationship between dihedral angle and J value for vicinal coupling, so that's this 1, 2, 3 bond coupling, is described by the Karplus equations. The dihedral angle is just the angle between these two. And we can see for very low values, so around 0, the overlap is good. These are parallel, and you get a nice big J value somewhere around 13. If, however, you flip this proton here 90 degrees, orbital overlap here is really quite poor, and you end up with a much lower J value, something around 2.5 perhaps. However, as we push on back up to 180, again, this is an anti-periplanar arrangement. This is favourable for overlap, and we again get nice big J values. Something I'm going to come back to in a later tutorial that I'll mention just briefly here is that NMR is a slow technique. So what you usually, although not always, observe is actually an average of conformations. And in the case of a chain like this, the observed J value is consistent with an average of the most common conformations, the conformations the molecule spends the most time in. And that'll be 60, 180, and 300 degree conformations. So you end up with a J value actually somewhere around 7. If, however, it was fixed in a ring system, then it wouldn't be able to rotate, and we would be able to tell a lot about the arrangement of the protons from the J value. And just in general, coupling constants tell us a great deal about spatial arrangements. There are some other things that matter. Electrons on a carbon adjacent to electronegative element are pulled in closer and they're less available to facilitate coupling. This results in lower J values. So here we have the good overlap between this oxygen and this carbon, hydrogen, so on. And as a result, it really inhibits the coupling and you end up with a low J value between these two. If you actually take the same geometrical arrangement between the hydrogens here, but you move the oxygen into a position where it's less able to interfere, you get a much larger J value. I would point out though, this is still considerably smaller than you would have if the oxygen was gone entirely. So geometry still matters. The better conjugated the withdrawing group, the stronger the effect. Bond length is also important. So this shorter pi bond here is able to transmit the information between the nuclei more effectively than this sigma bond that you have in between here, and there's a big difference in the J value as a result. Angle strain could be considered a kind of special case of the geometry story, but here this is illustrated quite well by this series of cycloalkanes. You can see for the smaller rings, the more strained configurations, the protons are kept apart in almost a V shape, and if you imagine that there's very little opportunity for the bonds to really overlap in this arrangement. But as you make the ring larger, this angle, the theta and theta prime angles, shrink and the overlap is improved, and so you go from a J of 0.5 to 2 right up to a much more sizable 8.8 to 10.5 Hz observed in this system here, cyclohexene. Just one more thing I want to mention. This is true for homonuclear couplings. For heteronuclear couplings, for example, the hydrogen-fluorine coupling we saw earlier, you do have to consider the nature of the other atom as well. So fluorine will tend to produce larger couplings, aside from any other considerations. Now that we have looked at both intensities and J values with regard to the information they give us and how they inform us about the connectivity of our molecule, I'd like to introduce a formalism which is generally very useful, and this is the splitting tree. So the idea is that we mark the lines in our signal and we measure the gaps between them. And this gives us our J values, 7. And we can see that this one matches. We recognize the shape of the signal. The intensity pattern is correct. This is a triplet. And if we alternatively wanted to draw it as a doublet of doublets, we could say this is 7, and as it turns out, this is also 7. That's why it's a triplet. Here we can see that we're layering our couplings in the tree. To give you an example where the J values are not the same, here we have central green proton here. It has 2 ortho couplings. Here is the small coupling. And if we wanted to find the large doublet here, that would be the center point between these 2 signals that are split from it. However, we don't need to actually measure the center point because that spacing is the same as the spacing here. So we can take these lines or the equivalent of that signal and measure this, and that is our second J value, which is 7.5 Hz. We then move around to another signal. This could be the red or the blue. We have a large ortho coupling and a small meta coupling. Here is our small meta coupling. And again, we don't need to look for center points. We can measure the gap here, which is the same as that gap there. This gives us our larger coupling of 8 Hz. For a slightly more complicated example, this looks a lot like a sextet, but there are only 4 coupling protons. So this is a bit alarming because we know there should be 5 to get the correct intensity pattern. But then if we look at the intensities for a sextet, we should have 10 and 5 and 1. We can see the signal is not twice the size of that one. In fact, this is not a sextet, it's a doublet of quartets. So there is our quartet J value. We can distinguish that this is the quartet from the intensity pattern. And then to identify the second quartet, we can see that here we have the first 2 lines of a quartet. We would expect another 3 here. However, what we have is 4, and this is because the first line of the second quartet is being added on top, and so here is our J value, which is the equivalent of this space. You don't have to use the edges, so you could equally use that. Let's look at a different doublet of quartets now. This one has a small coupling and a large one. It looks much more like a doublet of quartets. Again, here is our small coupling. This is 3.5 Hz. And then we have a huge coupling, and it's much easier in this case for us to pick that out. These are all equivalent. They will all give us our second doublet coupling here. Now, you may have noticed that this is not technically a doublet of quartets. Actually, it should be a doublet of doublets with our large coupling from this geminal coupling here, and then axial equatorial and equatorial couplings to these other protons. However, these J values are close enough that they overlap, and we get something that looks like this doublet of quartets. Another doublet of quartets. This time, the doublet is the smaller coupling. So this is a proper doublet of quartets. This time, we have an axial equatorial coupling. We would expect this to be small. Remember that the angle is not ideal for orbital overlap, and so the J values are relatively small here. And here is the first line in our first quartet, but instead of having a 3 beside it, we have another 1, and this means that this is the second quartet, and so this time this is our doublet splitting, and if we want our quartet splitting, we're actually going to have to go to here, and that is this space, and it gives us a larger J value. And so we have the same 3 examples of the same signal here, and we can distinguish what they are and their connectivity from them, from the shapes and the J values. Here's yet another example. This differs from the previous only in flipping whether the doublet or the quartet has the larger or smaller J value. You can see you end up with a completely different pattern, again where it's something that looks like a sextet but isn't. And here the larger of the couplings is our doublet, and the axial equatorial and equatorial couplings that end up looking like a quartet are small, and so there is our quartet J value, and here again is our doublet J value. And these signals can be distinguished, and you can distinguish these connectivity patterns from each other based on these signals. So we're getting really quite a lot of detail about how the atoms in our molecule are arranged with one another. There are limits. There are limits to what you're likely to be able to personally work out. I would suggest not bothering with this one, for example. There are also limitations that you should bear in mind when you take real spectral data. These are simulated, and so they work out perfectly. There are other factors. Measured J values rarely match exactly because the lines are very thickness and they can become distorted. They can have other protons underneath, and they can display other phenomena that we'll cover in later talks, such as roofing and second order effects. That said, when you get good spectral data, it is quite often the case that you end up with quite distinct complex signals that you can interpret and tell you really quite a lot about how the molecule is connected. And this is the real advantage of NMR. There are other techniques that can inform us on functional groups or overall molecular properties. What the NMR gives us is the connectivity. I am, of course, available for questions, but here are some other resources that I think you might find useful.